seen that what are the different natural fractures, and we have seen that how we can see the different type of the natural fractures, how we can measure it, okay, and what are the different types of the natural fractures and the grid systems, and how they can be mapped, how they can be estimated, and how their impacts are on the gas sufficient capacity and the transport. Generally, this discussion is on the transport. So we have seen that how they can affect the transport properties, okay. With continuation of this, some of the factors, today we'll be introducing another factor which is more or less related to the earlier natural fractures, that is called the reservoir geometry, okay. The reservoir geometry, if you can, if from the earlier notes, whatever we have seen in the second and the third chapter, if you can visualize the CBM reservoir structure of coal matrix, the facelets and the buttlets, whatever you have learned now, then probably you will be able to understand that the reservoir geometry is nothing but the size, the shape, and the presence of the natural fractures of the open channels into them. Okay, these are comprising of the geometry. Okay, so from which direction the open channels are provided, not provided, it is naturally created during the qualification process or during the evaporation of the water and other fluids. So it is totally natural phenomena under the temperature, pressure, or other biological effect or the chemical effect. Okay, so we don't have any control onto them, but how they are going to see, suppose there are three axes and x, y, z, two horizontal direction and one vertical direction. So if you can imagine a block, a reservoir block or the coal matrix block in underground. So obviously, depending on the deposition, as the coal is a sedimentary rock, you can understand that depending on the deposition, if it is perfectly horizontal bed, perfectly horizontal deposition, then obviously there will be bedding planes in the vertical direction. As you move vertically, you will be experiencing different type of rock strata, which can be known by the borehole log section, and then there is some other rock type. So whenever we are going to look into only one single bed, suppose that there are shale, then your coal, and then the sandstone. Okay, so shale is comprising the roof, then your body or the working height is the coal, what you are going to extract, and then the floor is the sandstone. So in this case, in this individual bed zone, suppose if you are going to from top to bottom, obviously you are going to intersecting shale, then coal, then sandstone, so different layers. But if you are going to move horizontally in a single bed, suppose you are standing on the coal floor, standing on the sandstone floor, and working on a coal. Okay, so if you move laterally or horizontally or within the seam, so there is every possibility that you are not going to intersect any other rock type, but obviously of the same rock type, of the same coal, there may be different deep or discontinuity or the number or the frequency, everything will be different. So obviously it is a heterogeneous rock. Coal is obviously a heterogeneous rock depending on the deposition, and so this heterogeneity is going to affect. So we are going to study in the reservoir geometry how the formation, depending on the beds, depending on the bed formation or the qualification process, how the formation characteristics are going to affect the storage and the not storage, mainly the transport properties. Okay, so if you can see that, if you can imagine this three-dimensional geometry, you will see, you will be able to understand that the factors that have the greatest influence are the structural and the stratigraphic. Okay, So the structural means the way it has formed depending on the deposition and the qualification process, whereas the stratigraphic is the number of layers of the, it's something which is based on the deposition or the deposition environment. If you have studied the geology, you understand what does it mean by the word stratigraphy? Anybody or everybody? Do you understand the term stratigraphy? Please respond. Do you understand the term stratigraphy, everyone? No response? Hello? Please respond.
Yes, sir.
You are 31 student. You are 31 students are present in this class, and you have taken so much time to respond. Is it the way that you are just making it on and then left the computer, left from the classroom? Please don't do that, because you will be the worst sufferer. Okay. Anyway, so depending on the deposition and the way it has formed, so there are the two main items to consider. First is the structural thing, and second is the stratigraphic. Structural is more or less depending on the way it has formed, and stratigraphy the way it is deposited. Okay. So mainly these two, and then there is a lot of variation throughout this CBM reservoir. And obviously, this structural and the geometry, or this structural and the stratigraphical differences from place to place, they are going to affect the other properties, which in turn directly or indirectly affect the permeability of the CBM reservoir and hence the production from the CBM reservoir. Okay. Suppose suppose we are going to talk about the deposition. Okay. Sorry, we are going to talk about the structure. Now you have studied rock. You very well understand the concept of the chyle and the diane material. Chyle, and the diane, DIANE. Do you understand these small acronyms and their importance in the rock mechanics, the structural or the stability analysis? Chyle and diane concept. One is related to the most simple ore for designing. Another one is the field condition. The chyle is the continuous, homogeneous, isotropic, and linearly elastic, whereas diane means discontinuous, anisotropic, discontinuous, inhomogeneous, anisotropic, and non-linearly elastic. Depending on this type of two rock concept, okay, we are going to relate the chyle with the intact rock for doing these simplest assumptions for the laboratory and the design principle study, design analysis, whereas diane is more or less correlated to the field condition or the rock mass condition, where we are going to take the simplest form, and then we are going to add on the different concepts of the variation in different properties. And so we are going to get the complex nature of the in situ, and thus we are going to design taking all the concepts or all the nature of the underground rock conditions. Okay, so like that, the structure is going to vary. So in these three directions, suppose x, y, z, obviously the anisotropy is going to be dictated by this three-dimensional body or the generation of the rock. Okay, so if you can imagine the coal block, okay, you know that there is a bedding plane, there's a horizontal bedding plane, and then you have come to know about the CBM reservoir, from the CBM reservoir, that there is a face cliffs and the butt cliffs. But you have already seen that the face cliffs or butt cliffs are having some differences, some fundamental differences about their frequency, about their opening or the aperture, about their length or the extent or the consistency, about their infilling material maybe which is going to present. Okay, So all these things again going to impact the flow through these openings in the different directions. Okay, so if you have studied like the earlier discussions, if you have come to know about the different net or the mesh type of network of the fractures in the x, y and the z direction, so you will be able to estimate that okay, what will be the probable flow in those x, y, z direction based on the fracture presence. But how this fracture will come? This fracture will come based on the structural formation and based on the deposition. So obviously, if the geometry means the orientation, the direction, okay, and the stratigraphy. So as you have seen earlier, that whenever we are going to talk about the slope or the stability or the movement of the beds, we are obviously going to dictate about we are going to see about the deep and deep direction of the beds. Okay, so this deep and deep direction are nothing but the orientation. Okay, orientation, so that we can locate or we can identify that at which point, at which direction this particular bed is going to slide. Okay, so like this way, if we come to know, if we are able to know that what are the face slits and the butt slits total direction and how they are interconnected between among them, okay, face slits, butt slits and the tertiary slits, so this will give the geometry, okay, of the CBM reservoir. In the second case, the stratigraphy. The stratigraphy means different type of rocks. So suppose that if you are observing the borehole log section, you will be able to know about the depth and the thickness and accordingly the different rock type. Okay. Now when these different rock types are present, when the different rock types are present, you will be able to know that okay, depending on whether my strata is available soft or strata is available very hard, so you'll be able to understand that okay, based on this our hardness, our other parameters, the porosity and the permeability is obviously going to change. We will be not getting the same type of porosity and permeability what we are going to experience in coal than that of what we are going to experience in the shale or sandstone. Okay, for shale, you all know that depending on the bedding plane, shale is very weak along this bedding plane. You are just putting a tap with hammer, and then it will be fractured or separated. Whereas if you are going to if you are going to break it across the fracture in opposite direction, in perpendicular to the fracture, it will be very hard and you will not be able to break it. You can find that when you are going to apply the force, it may again break into the this direction along the or the parallel to the fracture plane only. So this type of anisotropy thing, okay, is obviously very much common in the in situ or in the field. So this concept is again you have to imagine from the point of the CBM reservoir. Okay. So in this following text, they have taken again the field experiences so as to give you the different idea and how you are going to suppose this geometry. Suppose there are some structural formation is going to take place. There are some stratigraphy, but then when you are going to do this borehole, when we are going to do the excavation, obviously we are going to apply the drill tool to cut it, okay, to apply the force, and that drill induced fracture are very much a new fractures are generated due to that drilling. There may be some natural fractures which is going to be deposited and generated during the form of the qualification or some obviously. Is it okay? Am I audible? Can you hear me?
Yes, sir.
Okay, okay.
Yes,
I
sir.
thought that sometime network has gone. Okay. So, whenever you have seen that this type of phenomena, so you'll be clearly able to understand clearly able to understand that what are the things that means if you are going to drill a borehole, so obviously the drill induced fractures is going to create some new fractures in different directions. Suppose you are going to drive a vertical borehole, then obviously you are creating a direct channel, direct open channel in the vertical direction. But what is happening to the x and y? Obviously there will be some radial cracks, okay, there will be some radial fractures, and it is not always possible that radial cracks will be created always perpendicular, just the way you have seen in the hydraulic fracturing process. Okay, it will not be perpendicular always. Why? Because if you can remember, in the hydraulic fracturing process we have taken some assumptions that the major principles and the minor principal stresses are perpendicular, and one of them are going to be parallel to the borehole axis. But that is an assumptions only. That may not be true all the way into the in situ. Why? Because you know that whenever there is a discontinuity, the major and the minor principal stresses are going to orient depending on the surface of the excavation. Do you understand this, all of you? This is somewhat a complex thing, but I don't know your rock mechanics classes, whether you have learned it or not. Do you understand that depending on the excavation surface, the major principal stresses will be oriented parallel and perpendicular to the surface? Do you understand this? Do you know this? Hello? Hello?
Yes, sir.
You can understand this, what I am going to tell?
Yes, sir. Yes, sir.
It's, if you are not going to respond now, I'll be teaching by myself, and in the next time if you are having any problem, you can, if you are going to ask me, I'll not be able to correlate, because I'll think that okay, you are not very much giving attention to the class time, and that's why you don't have the end to attend the class sincerely. Okay. Anyway, so whenever you are going to visualize this type of thing, you will be able to understand that how this borehole drilling is also going to generate some fractures, which are the induced fracture. And for this some of the fractures, earlier existing fractures, they can be interconnected, they can be overlapped, or they can be extended. Their aperture can be extended, and so the directional variation of the permeability or the porosity, okay, obviously is going to change. So again, depending on this, the differences for the properties, in the case of the flow properties, in case of the porosity and the permeability, because these two are the main important forces, main important parameters, not the forces, to cause. Again, to give you the idea about these two phenomena, the structural geometry and the stratigraphic, I'll request you to go through the test and try to understand this figure 412. I hope you all can see it clearly. Figure 412 is going to describe you that how the different formation and the structural differences are going to affect the permeability. Here you can see that they have driven three different boreholes, A, B, and C. Okay, and you can see that there are the blackish deposit are coal, and the more lighter are the different type of rock. Okay, so you can see that they have given three boreholes, vertical boreholes. There is a fault. There is a different layer at the bottom plate. Okay, and there are 1, 2, 3, 4, 5 maximum coal seams, and more or less you can see that the more or less the seams are considered to be horizontal seam. Okay. Now, if you can see the different borehole logs with this view, if you consider the different cross sections or different borehole logs of A, B, C, obviously there are some differences. Okay, let us point out what are those. Suppose for A, you can clearly see that there are the 5 coal seam intersected at some regular depth. The first one from the topmost, as you are going down, the first first 4 seams are more or less equal distance apart, whereas the fifth seam, the bottommost seam from the well A, is very much close to the fourth seam. Okay, whereas in case of B, and there is and the well A, there are 5 coal seam, and all other in between are the different rock layers, or maybe the barren zone, if you can imagine. Whereas in well B, you can see in the well B there are different type of the coal seams available with a different variation, thickness variation, and there is also some different type of rock, and there is a sandstone belt also they are going to intersect. Okay, and you can see how the thickness of the coal is going to be varied here, and at this small thickness it may not be economic. If you are going to mine, it may not be economic, or if you are going to do the gas production, okay, from this, it may not be even economic also to arrange all those things, pipelines and everything. So and obviously there is a chance that if you are going to take this thing as a whole block, so there is a dilution of the grade. Can you see that? Okay, in this area also. In the third case, the well C. Well C, you can see that, okay, it may not be having that much complexity of well B, but obviously there is a one seam is absent. And as you can see that the seam location, if you are going to plot, the first 3 seams, first 2 seams are maybe related to the borehole A cross lock section, but then the third one is somewhat, third and fourth is somewhat uplifted. So you will be interpreting that, okay, there may be a rise, okay, there may be a rise, and that's why the coal seams are uplifted, or maybe there is a fault. As you can see that there is a fault, and the left side the beds are going down, the right side the beds are going up. Can anybody tell me what type of fault is this? See the figure and see the fault and the bed separation of the bed movement. Can anybody tell me what type of fault it is?
Sir, tensional fault, normal fault, sir.
Normal fault, yes. Why? Because if you see from the top view, a normal fault will be having some barren zone, whereas if it is a reverse fault will be having some overlapping zone. Okay, so remember all those things. So top view and the front view, so you will be able to understand these things clearly. Okay, now so you can understand very well that how the structural and the deposition environment are going to affect this deposition and this geometry, and again how they are going to define the parameters of the flow and how they are going to control the flow. Okay, so this is going to give you some idea. Okay, please go through the text. They are also going to discuss these things in detail in the following text, and I hope at this point you will be able to understand this. So the major variations, okay, major variations, again you can see that between these 3 boreholes, it is more or less equal, the separation distance or the frequency with per meter. If you can see the separation distance or the spacing of this borehole A, B, C, it is more or less equidistance. That means distance between AB is equal to distance between BC, whereas this may not be all the time. Okay, this may not be all the time. So now again, going back to a rock mechanics class, you have seen, considering the chapter of the stresses around mine excavation, considering the chapter of stresses around mine excavation, you all have studied how the stresses are going to vary, the radial, tangential, and the differential stresses, or the tangential or the shear stresses are going to vary in the boundary, and we have also taken the distance as you move in the lateral, horizontal or the vertical direction from the center of the excavation. Now this excavation size, it may be rectangular, it may be square shaped, it may be rounded corner, it may be circular or elliptical. Okay, and based on that, you will be able to understand. You all have studied that. Based on that also, the zone of influence, for each borehole to the surrounding rock strata is also different. Okay, and it is not going to depend on the size. As you have seen earlier, size is not that much critical because size is not coming to the parameter into the stress calculation, but it is always the shape. The shape of the excavation is going to impact much more. Okay, it's going to dominate. You should understand. Okay, so here also you can see the well geometry. Now the different thing, you know, the reservoir geometry. Okay, so now the well geometry. If you are going to do the borehole, how much you are going to design the boreholes, how much you are going to put the boreholes, the borehole orientation, whether you will be putting a vertical borehole, whether you will be putting an inclined borehole, or whether you are going to put a horizontal borehole that we are going to do for the hydraulic fractures. So all of these are going to impact the reservoir geometry, because these boreholes, if you are going to draw, depending on the impact, they are going to create natural fractures. They are going to not natural fracture, they are going to intersect the natural fractures. Some of them going to extend the natural fractures, some of them are going to close the natural fractures. So obviously the opening, the permeability, the porosity, these are more going to be anisotropic in the reservoir. So that is the effect. Okay, so please go through this. Okay, they have nicely discussed with some field data, and I have also highlighted some of the important discussions. As you can see that the several causes of the reservoir heterogeneity are illustrated in this figure. Changes in the facies. Changes in the facies means that rock deposition or the formation can result in gradual permeability variations. Abrupt continuity changes result from the pinch outs and the offset across the faults. Rivers that cut across the organic deposits in the swamp cause the channel sandstone deposits that also reduce the coal continuity. Again, all of this discontinuity, they can be, they can be open channel, or they can be partially filled, or they can be filled discontinuity totally. Okay, so again, there is a lot of variations depending on what material is going to be deposited inside the discontinuity. Okay, so, all these factors are greatly going to affect the flow system or the permeability concepts. Okay. So what we can see and how we can measure, the most common well logs used for the geologic mapping are the density and the neutron or the gamma logs. Gamma logs I have shown you earlier, based on the gamma signature, or the density logs. Density log means the deposition. Density logs will directly give you the idea based on the rock characteristics, the formation, so that the density will be giving you the idea about the porosity presence or the permeability variations. Okay, that means how much compact the rock is. Okay, so these are the two common methods to get to know about the well logs, and from there you will be able to estimate about the fractures or the discontinuity, like in the reservoir, CBM reservoir. Okay, now there are some criteria that when you are going to take the interpretation from this geometry, you have to be very much careful. Okay, because you know that at different cases, depending on the data, there are two seams may be overlapped, or one may be going into the other for rock deposition, or for the rock geometry for the discontinuity also. There may be the cases that the discontinuity is going to extend, overlap, or going into one another. Okay, so this can be abruptly stopped, and this can abruptly stop, this can abruptly increase, this can abruptly create it from some point. So you have to be very careful when you are going to map this. Okay, the next parameter is very important, very important. It is the effective stress. It is the effective stress. Okay, now you all studied the weatherability effect, the environmental effect of your rock mechanics classes, and one of the environmental effect is for the effective stress. Okay, what is effective stress? It is nothing but the reduction in the vertical stress. Okay, That's why it is called the effective stress. Okay, whenever there is a dry season, in the dry season, whenever the rock is very much open, or rock is situated, a rock is not saturated with water, or the partially saturated with the water, then comes the concept of the effective stress. Why? Because of the vertical uplift force due to buoyancy forces. Okay, so whenever we are going to calculate the or estimate the permeability, obviously the pressure have to be seen, the stress component has to be seen. Okay, you can very well know that whenever you are going to do the triaxial test condition. Okay, triaxial test condition is the confined in situ condition where we are going to estimate the rock strength. Okay, that's why it is called the confined uniaxial strength. Confined rock strength you are going to calculate from the triaxial compression testing. Okay, there is a lateral forces. There are lateral forces surrounding the rock. Okay, and there is a confining force given by the fluid, and then there is a vertical load which is given by the correlated to the vertical stress or the overburden stress. Okay. Now, in the laboratory, we always keep the vertical forces, the load at failure, as the confining increases. You all know that the load at failure will also increase. So, the graph of the stress strain graph for a particular rock type is going to be sharper and going to be higher. The rock will fail at higher loads if you are going to increase the confining pressure. Okay, this thing you already know. But then comes the assumptions. In the laboratory, we have always seen that we are going to apply the pressure in the xy direction, and the z is the vertical direction. So xy direction, the lateral pressures are same, whereas in the in situ, in the field, this thing is not same. The two horizontal stresses h1 and h2, okay, are more or less different in most of the cases. If it is not in the hydrostatic stress condition, there are three different stress conditions. One is uniaxial, only vertical stress, no horizontal stresses. The hydrostatic stresses, where it is behave like an immersing a body into the water, and all the x, y, z direction, three directional stresses, principal stresses, are equal. Okay, so that is occurring at the greater depth, nearly 4 kilometer or 5 kilometer or even much higher. Whereas in between them, it is always the biaxial. Biaxial means the horizontal stresses and the vertical stresses both are existing. And most of the cases, it is observed that the horizontal stresses are not same in the two different directions. Okay, so obviously, if you are going to calculate the permeability, if you are going to calculate the flow, you have to see that what are the effective stresses values in the two different directions. And then comes again the effect of the geometry. You have seen in the rock mechanics class that the flow along the discontinuity is obviously higher than the flow across the discontinuity. Sometimes it is nil, sometimes it is zero. The cross flow is sometimes zero, depending on the other surrounding rock structure. Okay, so obviously, if you are going to calculate the effective stress, you have to calculate how you are going to see. You have to see the effective stress by the vertical stress and the pore pressure. Pore pressure means the water pressure or the fluid, which is if the reservoir is saturated with some pore fluids, that fluid pressure is to be seen. The vertical stress, as you know, that always going to be estimated by the depth. Okay, whereas the pore pressure is the pressure of the fluid or the water that is going to be exerted, that is going to be subtracted from the vertical stress. Okay, and here you can see a new term which is called the beta. It is called the Byers constant. Byers constant is generally taken as 1 depending on the geometry or the reservoir shape. Okay, this Byers constant is generally taken as the 1, but it is actually slightly less than 1. But for our understanding, for our better calculation, we are always assuming that the beta, the Byers shape factor, is always 1. Okay, so the net stress effect, net stress or the effective stress effect, it is that stress which is going to dominate or it is going to move the fluid. Okay, and so the based on the pressure gradient, the fluid will pass. So that's why the effective stresses is very much important. And as you all know that this effective stress is not happening for the cases of the shear stresses. Okay, this effective stress is not going to happen for the case of the shear stresses. It is only occurring in the case of normal stresses. The pore pressure has to be subtracted only from the vertical stress, as the uplift buoyancy force is always in the opposite direction of the vertical stress. Okay, now depending on this effective stress, so there are, if you have you can visualize that there is some gradient of this density. How to understand? If you are going to from surface to the underground, as you are going to increase your depth, you will be able to calculate the vertical stress by assuming the density of the rock. Now this density is again going to change. Okay, if this density is only for the rock, okay, there will be a separate density, where and if there is no water present, that will be separate density, and if it is totally saturated with the water within the rock, then this density will be somewhat different. Now, from the principle of reservoir engineering, which is beyond the scope of your knowledge at this point, there are two concepts. There are some guidelines, not concept. There are some guidelines that the hydrostatic pressure, there is a hydrostatic gradient. That means per meter or the per kilometer or per feet, there is certain rate of increasing the hydrostatic pressure. You can see here they have mentioned that it is 0.43 psi per foot, or in the SI system it is taken as 10 megapascal per kilometer. The hydrostatic gradient is taken as 10 megapascal per kilometer. Okay, whereas if no water is present, then this density gradient or the rock gradient, the overburden stress gradient, okay, this rock density is going to change as in 1 psi per foot, 1 psi per foot, or 23 megapascal per kilometer, 23 megapascal per kilometer. This is from the reservoir engineering principle. So I just need to mention you this. You please try to remember. I'm not going to discuss that detail about this topic, but which is only related, that's why I'm discussing. Okay, so from these two guidelines you can very well see that if you are going to plot depth and the stress, so we'll be getting two different gradient. One is for fluid or one is for water, hydrostatic gradient, which is somewhat less inclined, flatter than the density gradient of the rock, which is the steeper. Okay, so 1 psi per fluid and the 0.43 psi, or 23 megapascal per kilometer, or 10 megapascal per and 10 megapascal per kilometer. So the difference 13 megapascal per kilometer or 0.56 psi per foot. This is the difference. The rate of this effective stress will increase. Okay, because if you are going to neglect the pore pressure at each depth, you will be able to see how much this effective stress is also going to increase. So it is that effective stress or the net stress which is going to dominate to create the stability or the failure, again in combination with the horizontal stresses, because this is only for the vertical stresses and the effective stress is only related to the vertical stress and the pore pressure. Okay, so this is the concept, that whenever you are going to consider the effective stress, you have to consider the effect of this pore pressure and the density of the rock also. And obviously the density of the rock, that gradient is much higher than the water gradient or the hydrostatic gradient. Our next topic is the next parameter for which is going to affect the flow is the 3 parameter combined into one, because it is very interactive. Try to understand each of it: fracture system permeability, porosity, and the pore volume compressivity. Fracture system permeability, porosity, and the pore volume compressivity. Okay, how to understand this? Let us first try to understand each term. Fracture system permeability. The fracture system permeability means the permeability of the fracture systems. Okay, obviously the permeability in the fracture systems are much higher than the permeability into the cold matrix because it is a single permeability model. Remember always that single permeability model. So the fluid flow is not allowed in the cold matrix. It is only allowed through the fracture systems, and the fracture system can be surrounded by the cold matrix like a phase clits or the particulates or the tertiary clits. Okay, so this is the permeability of the fracture system. Next is the porosity. This porosity is not the cold matrix porosity. This porosity is not the cold porosity or the porosity which is occurred by the solid volume and the void volume or the intermolecular spaces. This is actually the porosity which is created by the separation or the aperture of the discontinuity surfaces of a single fracture, or the different collectively void spaces inside the fracture network. Okay, and this totally is going to define, because your CBM reservoir is having one part is the cold matrix and one part is the fractures. So now we are going to estimate the porosity of the fracture. That means in the solid CBM reservoir, how much is the void created by the fractures. But remember, the primary porosity is always how much void space is created within the pores. That is the primary porosity. It is the secondary porosity. And the third concept is the pore volume compressivity. Pore volume compressivity. That means if you are going to consider this matrix porosity, this fracture porosity, it will be able to give a volume. Okay, it will be able to give rise a volume about the total fracture volume, total empty volume within these fractures. And this volume, again, when you are going to varying the stresses, you know that depending on the stresses, tensile or the compression, the rock is going to behave as elastic, as an elastic fashion, and obviously it can extend or it can contract. So whatever the solid cold part are existing, separated by the discontinuity or by the fracture systems, it can be extended or it can be contracted based on the tensile or the compressional forces. Okay, so that's why the compressivity is again coming here. Okay, this compressivity is for the coal. If you are going to consider the compressibility of the gas, that is totally different concept. Compressibility of the gas, compressibility of the fluid, and compressibility of the rock. These three things, concepts are same, but the values are differentiating in a very high scale. For solid and liquid, it may be somewhat later. For solid, it is very less. For liquid, it may be somewhat increasing. But for gas, it is very high. Okay, for gas, it is very high. So that's why the bulk modulus, which will come into the play based on the pressure gradient, depending on the pressure, how much contraction or the extension the particle can experience. Based on that, this compressivity, this bulk modulus for each individual rock, fluid, or the water and gas will vary, and again the compressivity factor will also vary. So what we need to understand, at any direction, suppose we are going to consider the average permeability, as you can see, equation given as 424. If we are going to consider the average, the permeability, we have to consider the average permeability. Why? This can happen because a particular fracture with its progression, okay, it will not be always in the same x direction or the y direction. It can be, if you see the fracture broken surfaces, okay, if you can imagine the asperities, okay, the asperities of the broken surface is not only a straight line. Sometimes it is, if you see a front view, sometimes it will be just going up and sometimes going down, and then it is going to be moving like this. So its orientation, its direction is changing. Although you can see roughly it is in horizontal direction, but its direction is always changing somewhat from horizontal. Sometimes it will move 15 degree above, then 10 degree above, then 5 degree below of the horizontal, and like this way it will move. So here you can see this equation. Ka is the average permeability, and it is considered as root over of Kx and Ky. Kx and Ky are the two horizontal direction if you are going to consider x and y direction, and the z direction is the vertical, it is going as a vertically down. So it is the depth. So x and y, that means at particular direction, depending on a particular fracture, the average volume flow from this fracture will be also going to differentiated, will also going to be dominated by the two different permeability available in the two different directions. Okay, just like the concept of the Mohr circle, you have seen that whatever the fracture surface will be created, okay, whatever the fracture surface will be created, it is obviously going to be dominated by the normal vertical load and the confining radial load. Okay, and that's why in the triaxial compression you are going to get angle beta of the fractures. In new plane, angle beta you are going to calculate as beta is equal to 45 plus phi by 2, where phi is the angle of internal friction. If you can remember the Mohr Coulomb failure criteria, I am going to relate that for your better understanding. So for any average permeability, you have to consider this. Okay. Otherwise, if you are only going to get only one directional concept, then it will be wrong, because the rock is anisotropic, and that's why it will be having a component of other directions also, just like the stress matrix. Okay, the fashion it is there, so that's why it is there. Now there is a lot of discussion required for this individual three system. It is going to be depicted as one, but to understand these three will require time. So for today, I'll stop here, and in the next class I'll be starting with this. Okay, because it is a quite important discussion, and I don't want to finish it in just like anyway. Okay, anyway to kill the time, or to quickly end it up. Okay, so we'll start on Thursday from this discussion after this equation. Okay, and for today, if you are having any question, you can ask me. Anybody, if you are having any question, you can ask me now. Let me stop the recording first.